Good morning from here in Indiana, whatever time it is, wherever you are. I know I have students all over the globe. Today I'm going to talk about Chapter 19, the circulatory systems, specifically the heart. In Chapter 18, we discuss blood, and today the heart, and then next time we will talk more about the blood vessels and circulation. Okay, I have already posted for you a list of figures and tables that I wish you would get printed. I've also mentioned, or maybe I didn't mention it before, but at the end of each chapter is a good study guide. I want you to print that off too. That'll get you a couple of extra points, I'm sure, on any tests. Okay, starting in section 19.1, a general overview of the cardiovascular system. Oh, if this lecture gets too long, I will break it up into two parts, and you will see chapter 19.1 and 19.2. We'll see as I go along. Okay, the general circulatory system, or the cardiovascular system rather, consists of the heart and the blood vessels. There are two major circuits. If you look on page, figure 19.1 on the next page, you will see the pulmonary circuit that takes blood from the right side of the heart, sends it to and through the lungs where it releases carbon dioxide and picks up more oxygen. Then the other circuit is much bigger. It is called the systemic circuit. This takes blood from the left side of the heart, sends it to every other cell in the body, very oxygen rich, and then returns the blood to the heart with very little oxygen and a lot more carbon dioxide. Okay. The heart is about the size of a person's fist, no matter if you are a woman or man, or if you are a child. And it sits, if you look on figure 19.2, it is basically under the sternum for a little extra protection, and just above the diaphragm. This is the normal position of the heart. And you can see more about the position if you look at parts B and C of that same figure. Let's look at some different protection layers around the heart. The heart is enclosed in a double-walled sac called the pericardium. The outer wall is called the pericardial sac. The inner wall is the visceral pericardium. The visceral pericardium is very, very close around all parts of the heart. It binds it quite well. In between, there is a potential space. This pericardial cavity normally contains between 5 and 30 mLs of blood. If you remember that 5 mLs is the same as 1 teaspoon. So that'll give you a little better idea of how much fluid there is there. And this is just to allow the heart to beat well and not to rub on anything else. Look now at figures 19.3 and 19.4 on the next two pages. Here we'll start talking about the gross anatomy of the heart. The heart wall consists of three different layers. The epicardium is a thin serous membrane on the external heart surface. Then the endocardium is a very similar layer lining the inside of the heart chambers. And then the myocardium is consists of the muscle itself, all of the cardiac muscle cells. It is by far the thickest and the strongest because it is the layer that does the pumping of the heart. The heart has 4 separate chambers that you can see best on in the real cadaver heart on figure 19.4, and then in figure 19.7. All the blood returns in through veins into the right atrium. It is collected there and then and then passes through a valve into the right ventricle. The right ventricle then, during systole, when it pumps the blood out and into the pulmonary circulation. After the blood returns from the lungs, it goes into the left atrium and then into the left ventricle. The left ventricle pumps the blood out through the aortic valve to the entire rest of the body. The left side of the heart and the right side of the heart are separated by layers of muscle septum. The intraatrial septum is not very thick because there is not very much pressure built up in either of the atria. The interventricular septum is quite thick and much more muscular because the ventricles generate a lot more pressure and pump blood with much more pressure. There are 3 separate valves, not 4, but 3 in the heart. The blood, or the venous blood, returns to the right atrium, and there is no valve there. But then the blood flows through the right atrioventricular valve, also called the tricuspid valve, into the right ventricle. Blood returning from the heart passes into the left atrium. And again, there is no valve there. But then there is a valve, the left atrioventricular valve, also called the mitral valve, that blood must flow through in order to get to the left ventricle. Then finally, there is the aortic valve through which the blood flows from the left ventricle to the aorta and then out to the remainder of the body. On pages 714 and 715, you will see several sketches, one picture of the surface anatomy of the heart in 19.5, and then in 19.7 you will see the internal anatomy and the position of the valves. Remember that there are only 3 valves. Okay, now you will most likely be asked on one of your tests to be able to trace the pathway of the blood as it goes through the heart. This you will see very easily in figure 19.9, and the different parts are labeled 1 through 11. These are the different pathways that the blood goes through in order to finally leave the blood, or to leave the heart. Now, how does the muscle of the heart itself receive its blood? There is what is also called coronary circulation, and you will see it in figure 19.10. Just after the aorta leaves the left ventricle, it gives off two extremely important small arteries, the right coronary artery and the left coronary artery. These supply all of the muscle cells in the heart. The right coronary artery branches into a right marginal branch and a posterior interventricular branch. The left coronary artery branches into the anterior interventricular branch, also called the left anterior descending artery, and a circumflex branch that wraps around the heart. The anterior interventricular branch is probably the largest of the coronary arteries and the most important. If blood is blocked for some reason in that left atrioventricular branch, a myocardial infarction occurs with death of the many cells and death of the heart itself. If you will take a real quick peek at the figure 19.22 on page 739, you will see a coronary artery that is almost totally blocked by some material primarily made out of cholesterol, and then some platelets that join in, and finally can block one of these arteries totally. There is, of course, venous drainage also from the heart muscle, and you will see that in figure 19.10, and some listing of the names of the veins on page 719. Now let's go from the gross part of the heart down to looking at the cardiac muscle and then the cardiac conduction system. Cardiac muscle is one of the three separate types of muscle in our body. It is, of course, not voluntary. It beats on its own, and it has a very important feature in that it is described as being autorhythmic. That means that it will depolarize and then contract on its own. This is how the pacemaker part of the heart functions. We will see that in just a couple minutes. The heart muscle itself is striated, but it's not as prominent because the muscle cells are very irregular in cardiac muscle. You will see that there is a feature called intercalated discs that hold the cardiac muscle cells together. Much pressure is built up, so these cells must be very tightly bound to one another, and that's how it's done. Cardiac electrical system, or the conduction system, is shown in figure 19.12 and a discussion on pages 721 and on several pages after that. The initial pacemaker that sets the original or the initial heart rate is found in the upper part of the right atrium. It is labeled number 1 in the figure 19.12. it beats somewhere at rest at around 70 or say 60 to 80 beats a minute. It is innervated by nerves from both the sympathetic and parasympathetic nervous system. The sympathetic nervous system, if it is stimulated, will cause the sinus node, or the SA node as it's also called, to beat faster. The parasympathetic branch will cause it to beat slower. Note also that the sympathetic branch causes a more rapid heart rate, but it also causes the heart muscle to beat much stronger. The original depolarization then comes from the sinoatrial or SA node. You will also hear this called the sinus node. This is the pacemaker of the heart. And in figure 19.13, page 723, you will see how this pacemaker potential changes on its own and how action potentials are generated. When it depolarizes completely to a little positive, just a little bit past zero of the membrane potential, this action potential spreads through all of the muscle fibers in both atria at almost the exact same time. Then this depolarization reaches another node that's called the atrioventricular node, and it is located in the septum, the interatrial septum, very near the right AV valve. This slows down the depolarization just a bit so that the atria are able to contract first before the ventricles contract. After the impulse passes through the AV node, it goes into what are called the right and the left bundle branches. The right bundle branch goes to the right ventricle, the left bundle branch to the left ventricle. And again, these are depolarized at about the same rate, the same speed, so that the two ventricles will contract at the same time. The final part of the system consists of what are called Purkinje fibers, and these are very small nerve-like processes that pass from both of the right and left bundle branches into the muscle and cause the muscle cells to contract. Figure 19.4 now, a little bit more about the electrical activity. I mentioned already the sinus rhythm, as it's called. Your author says from 70 to 80 at rest, but rates of 60 to 100 are not unusual, just from the sinus node. In a very well-trained athlete, the resting heart rate can even be lower than 50 because the heart is so efficient. This sinus rhythm is also called the nodal rhythm because it's coming from the SA node. Figure 1913 again shows how the heart muscle that has an initial transmembrane potential of about -60 depolarizes on its own up to a threshold of about -40 millivolts. Then there is rapid flow of calcium and sodium into the cells, and there is depolarization. This causes all of the other parts that I mentioned to go through both the AV node, the AV bundles, and into the muscle cells. This has to be done in a very specific pattern, as I mentioned, so that the atria contract and the blood is able to completely fill the ventricles, and then the ventricles contract. Turning now to pages 724 and 725, I will talk very briefly about the electrocardiogram. It is called the ECG or sometimes an EKG, depending on how the word cardiogram is spelled. It's an electrical tracing that's taken from the surface, the skin over the chest, and it has a normal pattern, as you see at the top of figure 19.15. If you expand one section between one beat and the next, you will see it start with a P wave. This is when the depolarization is passing from the sinus node through the atria and depolarizing them. And then the QRS interval, or the QRS complex, this is when the electricity flows through the AV node and into the both ventricles so that they depolarize. So QRS is when the ventricles are depolarizing. Then there is a slight resting phase, the ST interval or QT interval, depending on which way you want to read it. This is the time when the ventricles relax. The T wave is the actual repolarization of the ventricles. The repolarization of the atria occurs during the QRS complex, and you really don't see it. Figure 19.16 is an excellent set of figures that shows the relationship between the ECG to the electrical activity and then the contraction of the myocardium. If you trace that through, you will see one complete cycle. At the bottom of page 727, are some different EKG readings, or 4 of them are abnormal. Part A is the normal sinus rhythm. B is ventricular fibrillation. This is a dying heart. And then there are other rhythms that you can see in the EKG that need to be treated with something very, very quickly, because the heart muscle will not beat efficiently with any of these other abnormal rhythms. Section 19.5, blood flow and heart sounds. I'm going to leave that mostly for you. I want you to have printed off figure 19.19 so that you will see again the heart, or the way that the blood flows through the heart and through the different heart valves. Just below that figure, you will read about how heart sounds are made in the heart. Now, turn next to figure 19.20. Do I expect you to memorize this? Certainly not. I had to memorize this when I was studying the cardiovascular system during my first year of medical school. this is an excellent way to learn about the heart, because you can see the pressure generated in various chambers, the volume in various chambers, what you would see on the ECG. You would see heart sounds and the phases of the cardiac cycle, all one right above the other. So at any instant, excuse me, you can know what is happening. This is an excellent picture, and if you do go into medical school, nursing school, PA training, you will have to learn more about this. If you look at the page 733, you will see some of the volume changes in the heart during one complete circuit. Actually, not very much blood is pumped out of the heart during any one systole, only about 70 milliliters. Cardiac output is a way of measuring whether the heart is working correctly or not. And the cardiac output is measured by taking the heart rate in beats per minute and multiplying by the stroke volume. And that is the amount of blood that is actually pumped out of the heart during each contraction. You can, with knowing cardiac output, I mean, it's very difficult to obtain because you cannot tell the stroke volume without doing some sort of an intervention inside of the chest wall. But it is possible for cardiologists and nurses to do this in coronary care or intensive care units in hospital. A couple of definitions. Tachycardia is a persistent resting heart rate above 100 beats per minute. It is caused, your author states, by stress, anxiety, stimulants such as coffee, cigarettes, or even fever. Those of you who have children, if your child has ever had a high fever, you would note, if you had listened to their heart or felt their pulse, that their heart is truly pumping rapidly. In general, for each degree of fever, the heart rate goes up about 10 beats per minute. Bradycardia, on the other hand, is a persistent resting heart rate less than 60, except in a well-trained athlete, and then it would be less than 50 or possibly 45. There are different ways of changing the heart rate. One we mentioned with using stimulation from both the autonomic nervous system, the sympathetic and parasympathetic parts of that autonomic nervous system, and then by chemicals that are put into the body. I'm going to stop with that and see that, oh, I only took 30 minutes. I don't want to bore you, and I do expect you to use this, my lecture, only as an adjunct to your reading and looking at the pictures. If you do all of this together or individually and do it several times, I can almost assure that you will get an A in this course. Thank you very much. Next time, pretty soon, we will get into chapter 20, which is called The Blood Vessels and Circulation. Thank you very much.